if we have a mass m moving on a circle, angular velocity omega, what's the kinetic energy of the mass? Well, kinetic energy is 1/2 mv squared. The speed of the particle is angular velocity times the radius of the circle, which is something I hope is becoming second nature. So the speed would be v, which would be omega a. Then, simplifying this expression, we find the kinetic energy is 1/2 m omega squared a squared. Okay, so that was easy enough. Now, if we have this some small mass on some extended object, some object rotating about some axis of rotation at a distance r from the axis, what is its kinetic energy? Well, clearly it's just going to be what we got up here, except we're going to have a delta m, but the angular velocity is still going to be omega times this distance. Now it's going to be omega r instead of omega a, but that's not a problem. So we get kinetic energy is 1/2 mv squared, which is 1/2 delta mv squared. This is a small mass, small increment of mass within a larger object, okay? And we replace v with omega r, and we get 1/2. And the way I've arranged this, and clearly this arranges to the form I have here, and I think it should be legible, 1/2 times the quantity delta m r squared times omega squared. That would be the kinetic energy of a single mass increment. Now if we want the kinetic energy of the entire rotating object, well, we have to sum all these up, meaning we sum this up over all tiny mass increments delta m, each having potentially different distance from the center, because there are many different distances from the center throughout this object. So we're going to sum up contributions of this form. Well, the one thing we can see about this is omega, which is the rotational velocity of the object, the angular velocity of the object's rotation, is the same for the whole object. So it factors out of this sum, and we find that the total kinetic energy is just 1/2 omega squared times the sum of your delta m r squared. And for this reason, we define a quantity that's equal to the sum of the delta m r squareds, and that quantity we call I the moment of inertia. We're motivated, if we develop the idea this way, by the fact that kinetic energy is 1/2 mass times velocity squared. This is an angular velocity. We have a 1/2, so whatever this is, it kind of takes the place of mass, doesn't it, in the kinetic energy formula. So the kinetic energy is then, I didn't leave myself room to write this, but kinetic energy is this sum, which is this, where I is defined as the sum of all your delta m r squareds. This is your moment of inertia. Now, of course, this is only approximate at this point. I is actually equal to the limiting value of this as your delta m's approach 0. I didn't write it that way, but I could say the limiting value and that L just didn't come out right. There's a rough spot on the board. I is the limiting value of this thing as your mass increments approach 0. This is your moment of inertia. So we're going to calculate the moment of inertia for the foam disk. Now that's going to be a little bit of a involved process, and it'll illustrate how we use integration to find moments of inertia. But what we have we're going to assume we have 15-gram masses. And let's see, I should have a foam disc within reach here, but I think it's been moved. Okay, well, it doesn't matter. We know what the foam disc looks like. And I'm going to break this video at some point. I'll pull one out and show you exactly. We have 15-gram masses, and there are 4 of them. We have 4 rings of masses with 4 of those masses in each ring. So we have 4 15-gram masses at 5 centimeters from the axis, at 7 centimeters from the axis, and at 10 centimeters from the axis. Meaning that the moment of inertia of all these masses is going to be what? Well, we've got to add up all the delta mr squareds, okay? Well, the 15 grams, we have 4 of them at 5 centimeters, so there's our mr squared, and we multiply by 4. And then 4 of them at 7 centimeters, 4 the same at 10 centimeters. We add all that up, we get 10,440 grams centimeters squared. Now we're assuming that all these are point masses, and they're small enough to be very well approximated as point masses, but that's not a completely accurate result. These distances aren't completely accurate either. They're pretty close. So I don't think there's more than a 2 or 3% uncertainty or error in this calculation, okay? So that's the mass of, that's moment of inertia due to the masses that are embedded in the styrofoam wheel. We still have to determine the moment of inertia of the styrofoam itself. So that's what we're going to look at next.